One of the most important things you can learn in linear algebra is about eigenvalues and eigenvectors. But these can be pretty computationally intensive, so you're going to want to take your time and make sure that you don't make any mistakes. Here's how they work. So if you're given a square n by n matrix, we say that lambda is an eigenvalue of A if you can find a non-zero vector v such that AV is lambda v. In that case, we say that v is an eigenvector associated to the eigenvalue lambda. Now in practice, a single eigenvalue will have infinitely many eigenvectors associated to it, and we'll see why this is true when we learn how to actually find eigenvectors. So to start off, let's see an example. If I give you a matrix, an eigenvalue, and an eigenvector, you can check that they satisfy the eigenvalue equation. So here's a matrix, an eigenvalue, and an eigenvector. Let's compute AV and see if we get lambda v back out. All right, so we'll just start with A times V, and we know how to work that out. It's just matrix multiplication. And notice that the result that we get out is, in fact, negative 3V, and that's what we expected since we were told that negative 3 is our eigenvalue. Now, of course, the real problem is determining eigenvalues and eigenvectors of a matrix, not just checking them. So how do we find them? Well, let's go back and revisit the original eigenvalue equation AV is equal to lambda v. If we pull everything onto the left-hand side, then there's this common, vector v to the right of everything. So we're just going to factor it out. But we have to be careful when we do that factoring, since we can't just write A minus lambda. A is an n by n matrix and lambda is a real number, so we can't just subtract them. But if we throw the n by n identity matrix in there, then we'll be good to go. So we're looking at for the values of lambda which make this equation true. The problem is that if A minus lambda I is invertible, then this only has the trivial solution v is equal to 0. And the definition of an eigenvalue says that our eigenvectors must be non-zero. Thus, we need non-trivial solutions to this homogeneous system, and that in turn means that A minus lambda I must not be invertible. Now, we've learned about a tool which helps us determine when a matrix is invertible. That thing was called the determinant, and so we require that the determinant of A minus lambda I must be 0. And this is going to lead us to a brand new definition. So if A is a square matrix, then its characteristic polynomial is the determinant of A minus lambda I. Now, I've called this a polynomial, but it's probably not obvious to you that it's a polynomial. But once we've done a few examples, I think you'll see that it is, in fact, a polynomial. So from our conversation above, the eigenvalues of A are the roots of its characteristic polynomial. So if we go back and we revisit the example above, let's try and find the characteristic polynomial, and from that, the eigenvalues of this matrix. All right, so the characteristic polynomial we know is the determinant of A minus lambda I. And if we work that out, we will get the following. Now, I'm going into a lot of detail here, but eventually you'll see that A minus lambda I just means that you introduce these negative lambda terms into the diagonal. We have a handy formula for the determinant of a 2 by 2 matrix, so we'll just expand that out, and that'll give us the following. And since we want the roots, let's see if we can simplify and factor this a little bit further. Okay, great. And the eigenvalues are the roots, and we can just read those off as being negative 3 and 12. So we already knew that negative 3 was an eigenvalue, but now we see that there's a second one as well, in lambda equals 12. And that takes care of the eigenvalues, but how do we find the eigenvectors? Well, for each eigenvalue, the eigenvectors are going to be the solutions to the homogeneous system A minus lambda IV is equal to 0. So a few notes here. The first is that for each fundamental solution, any scalar multiple of that solution is also an eigenvector. And for our purposes, we're going to consider these to be the same eigenvector. Now, on the other hand, a single homogeneous system could have multiple fundamental solutions, meaning that there could be multiple fundamental eigenvectors for a single eigenvalue. So let's go ahead and let's finish off the example that we've been doing. Let's find all the eigenvalues and eigenvectors for this matrix. So we already know that -3 and 12 are the eigenvalues. In fact, we already know at least one eigenvector for lambda equals -3. But let's check if there's any more. So we need to solve the homogeneous system a plus 3iv is equal to 0. And notice that this isn't lambda anymore, right? We know what this eigenvalue is, so we need to make sure that we use it this time. So here I'm going to write out the homogeneous system as an augmented matrix like we normally do. And with this choice of lambda being -3, we see that it simplifies very, very nicely. And we can put it into RREF just by inspection, no need for any row reduction. So we're going to let our second variable be our parameter, and we're going to write out the RREF system so that we can solve for x1. Thus, we can write out our entire solution in terms of our parameter. And we arrive at a single fundamental solution, namely the one that we already knew. Next on the block is lambda equals 12. So let's solve a minus 12iv is equal to 0. Once again, we're going to set up the augmented matrix. We see that this system, again, simplifies very, very nicely, and we're able to pretty much jump straight to our REF. x2 is, again, our parameter here, and we're going to write out the RREF systems so that we can solve for x1. And that allows us to write down the whole solution as follows. But I don't like that fraction in there. And we're allowed to take any multiple of this solution, so let's multiply this thing by 2. Now remember that we can check our answers using the eigenvalue equation. So let's let A act on our vector -1, 2 and work out the mathematics of this. And yep, we get 12 times our original vector out. So eigenvalues and eigenvectors are very important in both theory and application, and now you know how to compute them.